It's David Spears, civil engineering instructor at Texas Tech University, talking about CE 2301 statics. Got a rigid body 3D equilibrium problem to look at. It's kind of a little bit of an unusual problem. What we've got here is the rigid body is this bar ABC, and it's supported by a cable at CD, as it says, this cable, and a square collar at A that fits loosely over a smooth square rod. Well, part of the analysis of this thing is setting up a free body diagram, and I need to see what forces the supports replace. Well, the tension in the cable is easy. I got to think about what's happening at the square collar at A. Okay, so the only movement that collar permits is an up or down movement, and it is, therefore, that's the only force that it doesn't provide, only reaction force that it doesn't provide. So, if you look at that collar, it does allow, because it's a smooth rod, it does allow movement up and down. But it doesn't allow movement in the X direction, in the Y direction. So it does provide forces in those directions, in the X and the Y. And think about what kind of moment, rotation, it doesn't allow. It doesn't allow any rotation. Because it's a square rod, it cannot rotate about the Z-axis. So it cannot rotate about the Z. It cannot rotate about the X-axis, which would be like flopping up and down. So it doesn't allow this kind of movement about the X-axis. And it doesn't allow rotation about the Y-axis, which would be twisting or torquing. So, as I think about what it doesn't allow, those are the forces that it does provide. So, the first step on these problems is always to do a free body diagram. And so a free body diagram of this thing looks like, draw it right here. There's the bar. The easy part is the cable, TCD. Then at A, let's look at the support reactions there. I said it does allow motion in the Z direction, so there is no AZ. But it doesn't allow movement in the Y direction, so I put an AY on it, in the positive Y direction. It doesn't allow movement in the X direction, so I put AX on there. And then it doesn't allow any of the three directions of rotation about any of the three axes, so I'd put that MZ like that. I would call it MAZ, which is a resistance to rotation about the Z-axis. It doesn't allow rotation about the X-axis, so I put that, draw a little curved arrow around it, that's MAX. And it doesn't allow rotation about the Y-axis, so I might show it like that. Call it MAY. So we'll talk about more about these forces as we sum them all up and write them all out. And then finally I have the applied force, which is this F, this 200I and negative 500K. So I would probably write it as F equals, I don't want to miss that 0 in the J position, so I'd write it as F 200I plus 0J minus 500K newtons. So once I've got a good free body diagram drawn, I'm ready to get everything in Cartesian form. So I need to get the coordinates of all these points. And so start up here at D. D is at negative 1.5 in the X. 0 in the y and 1 in the k, in the z direction. C is at -1, 2, and 0. B is at 0, 2, and 0. A is at 0, 0, 0. And that's the 4 points that I'm concerned with. Now, I know I've got a tension, I've got a cable CD. I need to get that into Cartesian. So the first step is to get a position vector and then divide by its magnitude to get a unit vector, which are the components of the force. So I want a position vector from the point where it's applied, C, towards D. We would call that R d over C. Well, R d over C is just the tip minus the tail. So I've got -1.5 minus -1 I, got a lot of minuses there, plus 0 minus 2 J, plus 1 minus 0 K. So I simplify all that, that's -0.5 I minus 2J plus 1K. Then I want to get a unit vector, so I divide by the magnitude, which is the square root of the sum of the squares, 0.5 squared, 2 squared, 1 squared. That all works out to be the square root of 5.25. So I can just divide all these -0.5s by square root of 5.25, and that's the components of the tension in the cable. So everything else, I need to get some position vectors here in a minute, but I can now start writing out all my forces. I'm looking at my free body diagram, and I'm going to start with TCD. And so TCD as a force, as a Cartesian, is these components times TCD. So I've got -0.5 divided by the square root of 5.25. So these numbers work out to be -0.2182 I minus 0.8729 J plus 0.4364 K. And everything is times TCD, the force in the cable. These are just 0.5, negative 0.5, -2, and 1 divided by square root of 5.25. Then I have, looking back at my free body diagram, so that takes care of TCD. Then I've got the force in the cable, the force applied, F, which is just 200I plus 0J minus 500K. Everything's newtons. Then I have the forces at A. Well, I don't have an AZ, but I do have an AX I and an AYJ, 0 in the K. And that's all my forces. So, the way I like to write them like that in column form, I'm left with, this column is the sum of the forces in the X, this is column, sum of the forces in the Y, this is sum of the forces in the Z direction, sum of forces X, sum of forces Y. All of those columns have to add up to 0. So I'm just kind of mindlessly going on because I'm thinking, well, I got to sum moments about a point to eliminate unknowns. So I want to come back to this. Now I am summing moments about, I want to sum moments about point A. So I do that to eliminate the forces at A, and I'm left with everything that creates moment about A is a force that doesn't pass through A, so there's only 2 of them, plus the moments that occur at A. So I have the moment caused by the force F plus the moment, these are all Cartesian vectors, the moment caused by the tension in the cable, and the moments at A. So I might say it like that. Okay, so I need to think about what do all these mean. And what all these are is cross products. This is R cross F, and this is R, some other R, position vector, cross with TDC. And these are just the moments at A, MAX, MAY, MAZ. So now I want to write them out in a form that I can do all these. These two produce determinants, 3 by 3 determinants that I need to evaluate. So I can do all that, and I can write it in a column form like this. The sum of the moments about A, and that is the moment caused by F, which is a cross product, R cross F. Looking back at my free body diagram, I'm taking moments about point A, so I need this position vector like this, from A to point B. So I would call that RB over A. Then I have the moment, that's going to produce a 3 by 3 determinant. IJK on the top. The position vector from A to B is tip minus tail. A is at 0, 0, 0, so it's just the coordinates of B. So these numbers are 0, 2, and 0 for the position vector. The force is just this value up here, where I've written the Cartesian form of it, 200, 0, and negative 500. So I need to evaluate that. I'll do that here in a second. Then I have the moment caused by the force in the cable, TDC. That's another position vector. R, in this case, from A to C. RC over A is what we would call it. And once again, A is at 0, 0, 0, so it's just the R is just C over A crossed with TDC, which is a 3 by 3 determinant that looks like this, IJK. Negative 1, 2, and 0, and the components of the force in the cable, which I have written up here, and it's negative 0.218, I'm not going to write the fourth digit, negative 0.873, and 0.436. Everything in this one's times TDC. I'll evaluate that. And then I have the moment at A, because the forces go away when I take moments about A, but not those moments. So what I do is I evaluate this out. Y'all know how to evaluate determinants. I end up with negative 1000 I plus 0J and negative 400 K for the MF moment. These are all units of Newton meters, because they're moments, force times distance. Then I've got the moment caused by the cable force, and that's going to be, I'm going to show you there's a quicker solution to this. Some number I, some number J, as I evaluate that determinant, some number K, and those are also Newton meters. Then the moment caused by the force, the moments at A is just, I have moments in all three directions, MAX in the I, MAY in the J, MAZ in the K. Okay, similarly, the way I arranged it up there for the forces, this column is the sum of the moments in the X direction. This column is the sum of the moments in the Y. This column is the sum of the moments in the Z. Okay, so everything in here down here has TDC as an unknown in it. So as I look at this, each column sums to 0, but the problem is I've got 4 unknowns, MAX, MAY, MAZ, and the force in the cable. So I've only got 3 equations. I can't solve that. So I think, well, there's got to be a better way. Maybe sum of moments is not the way to solve this directly. That's not the first step. So that takes me back up. Let's look at this determinant here for the sum of the forces. What I've got is this column, the sum of the forces in the x direction, and I've got 2 unknowns, TDC and AX. Some of the forces in the y, same situation. But some of the forces in the z, I only have 1 unknown because AZ is 0. So I can solve that column directly. What a fool I've been. I could have solved this because all I want to know up here is the tension in cable CD. So if that's all I want to know, then I can solve that. I can rewrite this equation. Sum of the forces in the z direction, I'm rewriting that equation, is 0.4364 TDC minus 500 is equal to 0. So I rearrange that and I see that TDC is positive 500 divided by 0.4364, and that works out to be the magic number of 1146 newtons. And there I've got my answer. I could have solved it without even looking at the moments. Now, if I want to know the moments at A and the reactions at A, I still need to solve all this stuff. But once I know the tension in the cable, I can plug all those values in, and now I can do sum of forces in the X, and that's equal to negative 0.2182 times that 1146 I just figured. I'm just doing this column right here, plus 200 plus AX. That makes AX equal to, you do all the math and it works out to be positive 50 newtons. Do the sum of the forces in the Y, and I can solve for AY by plugging in what I know there for TDC, and that gives me AY, you do the math, is equal to 1,000 newtons. It's just 0.8729 times 1146, and that's what AY is equal to. Now if I want to know these moments, I can go down here, and instead of having these variables in this determinant, I really have these numbers. I can solve for those, the X, Y, Z components of the force in the cable. And that works out to be negative 250, negative 1,000, positive 500. That makes that determinant a lot easier to solve, and that makes these numbers just numbers, not variables. 1000I, 500J, and 1500. That can't be right. Oh yeah, it is right because that's evaluating the determinant. So now I can just do the sum of moments and solve for MAX. I can see I've got negative 1,000 and positive 1,000, so MAX equals 0. I'm just solving that equation. Solving the sum of the moments in the Y gives me that MAY is equal to negative 500, because it's just that value right there, which is positive, but then I take it to the other side of the equal sign, 500 Newton meters. And MAZ is just summing this column, setting it equal to 0. I get MAZ, I got positive 1,500, negative 400, positive 1,100. That makes this number negative 1,100 Newton meters. And so I can solve it that way. So this is one of those rare cases where some of the moments doesn't really help me because I have these 3 unknown moments at A. And I have enough equations, though, in the sum of the forces to solve for the force in the cable and then those two reactions, and then I can come down here and do these other ones. Fun.